Welcome. We're going to talk about Chapter 7, Petroleum. Now, most of the energy that we get nowadays comes from organic matter or plant-based fuel, like wood. Our natural gas, our coal, our petroleum, all of these are examples of fossil fuels. Fossil fuels, of course, are fuels formed from the partially decayed animal and vegetable matter of living things that inhabited the earth in eras long past. Just in the 1990s alone, we got 85% of our energy in the US from fossil fuels. Of course, more updated number in 2020, we still get 79% from fossil fuels. So while we are improving, it's not that much better. Not only is petroleum and natural gas fossil fuel, they are a building block for a large number of synthetic chemicals that we need. All the plastics we make and polymers are going to be made from fossil fuels. We're going to break them down, as we'll see later, and build them back up in a very special way. But that's for another chapter. Petroleum in itself comes from the Latin petra, which means rock, and oleum means oil, meaning that we originally got this as oil digging in the rock, in the surface of the earth. So you notice a lot of these names become common nowadays are all from Latin or Greek origin for the most part. We get a lot of the petroleum from crude oil, which we can dig up from the ground. Still, 35% of all of our energy contains many hydrocarbons, such as natural gas, kerosene, heating oil, jet fuel. All of this are found within crude oil. We're going to talk about it a little bit later, how we separate these various components through distillation. Distillation is the process of purifying a liquid by boiling it in one container, condensing its vapors to a liquid, and collecting the separated condensed liquid in another container. Basically, two or more liquids are mixed together, and we separate them based on their boiling points. We're going to start this chapter by doing a demo of this, where I try to separate diethyl ether, methanol, and water. So I have here a mixture of diethyl ether and dyed green water. I'm going to attempt to add some dyed orange methanol to the mix. Because of the polarities of all three, they're now perfectly mixed together. We're going to attempt to separate them through distillation. So I'm going to now attempt to distill this. I'm going to travel up this flask to here. It's going to hit the condenser. It's going to cool down because there's cold water flowing through there and go all the way to that flask. And if done properly, I should be able to separate the three components. Place the heating mantle underneath. Now it's just a matter of waiting. Ethyl ether and the methanol are particularly volatile, and so they shouldn't hopefully take too long. Of course, they're also incredibly flammable, which is why I'm requiring a heating mantle rather than a Bunsen burner or something like that. The advantages of putting the thermometer up there is you can see what is the temperature of the gas that travels up. Trying to get boiling. See, it's boiling and condensing back down the sides. But if the gas gets hot enough to reach all the way up there, it should start cooling and traveling down there. Ether is getting stuck right there, but it's slowly traveling down. So it's leaving the green dye behind and traveling down. Yes, my precious, collect. pretty sure I collected my first fraction as it's cooled back down quite a bit of ethyl ether, but we'll see if I can get any more. This is hopefully fraction 2. See, it's very well condensing. It's around 65, definitely too low for water. I'm trying to collect a small amount of it at the bottom. We'll see how well this goes. My 2 fractions should be diethyl ether on the left and methanol on the right. The easiest way to test is to add a little bit of dye. The diethyl ether does not mix with the dye, but the methanol will. So if the dye dyes the whole solution, it has methanol. If it doesn't, it has only diethyl ether. See how the dye is kind of floating? There is just pure diethyl ether right there. So this second portion should be methanol. So if I add this and mixes, it's definitely methanol. Voila. Compare that to my other one. We have methanol. We've separated ethyl ether, methanol, and we have a majority of just water left in the tube. Had I kept going, I could completely separate the methanol from the water, and then I could even separate the water from the dye. But that doesn't serve our purpose. But this is the generalized idea of how you separate just about any liquids with different boiling points. Now, one of the things we get through distillation is various petroleum fractions, which are mixtures of components of petroleum, all with similar boiling points that are obtained through distillation of petroleum. Now, there are a variety of different chemicals, but we can say all the alkanes between, say, C5 and C20 are types of petroleum products. They can be separated based on their volatility. This is a term that will come up a lot this chapter. Volatility, of course, is the measure of the ease and speed of a compound's transformation from a liquid to a vapor. Basically, low boiling point molecules are very volatile. High boiling point molecules have low volatility. One of the compounds we separated, diethyl ether, is incredibly volatile. You can smell it easily because it is producing lots of vapor, even at room temperature, which can then be absorbed through your nose as aroma. Now, these petroleum fractions that we get from crude oil, crude oil in itself contain a variety of different hydrocarbon lengths, such as anything from natural gas, which is CH4, to hexacantane, which is C60H122, a rather large organic. Crude oil also can contain nitrogen, oxygen, and sulfur impurities in the presence of various organics, as well as some trace metals that are found with these organics. All these things need to be separated out before we can really use crude oil. The volatiles from C5 to C20 with various branching groups can all be useful fuels for us. In this chapter, we're going to understand how gas is prepared, how it's used and modified to make it work better. Why is this really important? Just looking in 2000 alone, the U.S. used about 7 billion barrels of oil in a year, 3 billion just as gasoline, which is more than a fourth of the rest of the world combined. In 2020, we're down to just a mere 6.6 billion barrels. However, that's largely due to COVID shutting things down. So we expect to be back up each year. It seems like our dependency on oil grows. Now, what is the main use of oil. How do we use this gasoline? We use it mainly in an engine. Now, in order to understand its usage, we need to understand how an engine works. We're going to say a 4-stroke engine here. The first thing, the key turns ignition that allows the battery to give it the motor energy to start cranking. And from there, we have the 4-stroke engine works. It's called a 4-stroke engine because to complete a cycle, it has a downstroke followed by upstroke and then a downstroke and then upstroke to get back to the original point. The first stroke is the intake stroke, where we have the far left. The chamber is essentially empty. There's just a little bit leftover gas. The downstroke allows this chamber to expand to allow gas in, at which point the valve allows the fuel air mixture in. The compression stroke, where it starts swinging back up, we're going to compress this down to a small volume so we can get the energy out. The smaller the volume, the more energy we can achieve. At this point, we're at the bottom of the compression stroke, which we do the power stroke. So the spark plug ignites the fuel mixture, which causes a minor explosion in here, which is going to push this back down, creating our power stroke. At which point, now that we're down here and we've achieved all the energy we can get, we upstroke back out to push the gases out and empty the chamber as the exhaust stroke. As long as we get more energy in the power stroke than we do lose in the compression stroke, we get a net positive gain in energy. Now, in an ideal world with ideal reactants, the products should only be water, CO2, but occasionally we have an incomplete combustion of fuel if there's not enough oxygen. In that case, we produce some amounts of carbon monoxide. And also, because of those nitrogen and sulfur impurities that are sometimes present in the gasoline, this will lead to various nitrogen oxides and sulfur oxides that are going to make up smog and acid rain that is produced by the engine. Now, gasoline is made of a mixture of hundreds of different alkanes, alkenes, and aromatic groups of various lengths. An ideal gasoline should deliver large amounts of energy for each gallon of fuel used. It should be reasonably inexpensive, and it should have volatilities in the range required by the engine. It would be bad if we had to fill up the tank twice a day because it ran through gas too quickly. It would be really bad if we had to pay $50 per gallon of gas because it was too costly. And of course, it'd be really bad if it was a sludge that didn't easily burn, if we couldn't get it to ignite. So it needs to be volatile within the range of heats in the engine. On a cold day, we need the engine to ignite, which is one of the problems we have with diesel fuels, which we may get into a little bit later. That diesel fuels are mostly liquid of higher chain length, and so they're less volatile. And at colder temperatures, they don't ignite as easily in cold days, and so you have to get the engine warm before they ignite. And so there's often a problem there. One of the things is we're going to have the right blend of alkanes and alkenes and aromatics to achieve this. We're going to mix carbons of different chain lengths to get some liquid fuel and some volatile gaseous fuel for that. We'll see right here on the right, as the chain length increases, so does the boiling point. That methane boils at -164, so it's almost guaranteed to always be a gas. Ethane, -89. Propane, -42. Butane, -0.5. Pentane is 36. Hexane is 69. Heptane is 98. So getting longer and longer chain lengths means it's heavier and heavier, and it boils at a higher and higher boiling point. Now, as you make isomers with linear versus branched chains, the branched chains almost always boil at a lower boiling point because of how they fit together. So butane boils at negative 0.5, but isobutane boils at negative 11.6. Pentane boils at 36. Isopentane would be 28, and neopentane would be 9.5. So by mixing different chain lengths, we can achieve a variety of some volatile gases and some not so volatile gases. And we need enough of this volatile gas so to mix with the oxygen to ignite on a cold morning. Now, if it's too volatile, we're going to get not enough oxygen in that mixture, and we're going to get incomplete combustion. This can lead to poor ignition, a roughness in your idle, poor gas mileage, and more importantly, you can achieve something called vapor lock, where essentially a bubble of this gas is blocking the fuel line, and your engine stutters and dies until the engine cools down and you can get that essentially gas bubble out. So this is something I didn't know until recently, that the gas is actually blended for each season and for the location. So if you traveled from, say, Tennessee to Oregon, you may want to, and you haven't filled up your tank lately, you may want to fill up your tank because you may be using gas that is not quite modified well enough for the temperature ranges you're dealing with. Chicago gas is going to be different level of volatility as New Orleans gas because you have higher heat down south. Like in the summer, you're going to have lower volatility gas than in the winter because you want gas that is the most efficient for the temperature ranges you have. Now, one of the key things that we need to consider is the compression ratio, which is the ratio of the maximum volume of the gasoline air mixture at the beginning of the compression stroke to the volume of the compressed mixture as the spark plug fires. Basically, to get the most amount of energy from the fuel, you want the highest compression ratio. In 1925, the compression ratio was approximately 4.4 to 1. But modern cars use anywhere from 8 to 10 to 1 and even up to 12 to 1 in certain better engines. This allows you to get higher amounts of power for the same amount of gasoline. You burn this, you get more power applied to the motor. You want to accelerate more quickly, you want a higher compression ratio. Essentially, how much energy, when this is compressed, the further this piston can expand, the more energy you can get. Now, in 1925, the air was compressed to about a fourth or a fifth its original volume. Now we've managed to compress the air down to a 1/10 of its original volume, and so we can get far more energy out. But this leads to the main problem here that we deal with gasoline. It's that knocking. You may have heard of this term, you may not have, but it's a rapid pinging sound that's produced by either pre-ignition of the gasoline or irregular combustion of the gasoline air mixture in the cylinders within an internal combustion engine. So essentially, this problem occurs under high power loads, like if you're accelerating, especially uphill, if you're towing something really heavy. It can even come on hot days while you're just going on highway speeds. Essentially, this is a bad thing. The normal combustion, the fire starts from the spark plug and radiates outward, a ripple in a pool. When this happens, you get the most energy applied to pushing the piston out. In a knock, if it's pre-ignition, like say during the upstroke, before it's at the maximum compressed ratio. So it's going to lose some of its power, as plus cause the piston to misfire, and that it's going to shoot down before it's really ready. And it could also just be it ignites not at the spark plug, but at various different places within the piston. And so either way, the energy isn't, you get multiple ripples. And so you actually lose some of the energy. All this knocking could result in just loss of power, poor mileage, but it could also pit or fracture the actual piston. So you could actually break your engine if it's knocking too violently. And at any gasoline grade, the higher compression ratio you have, the more likelihood of knocking. So if you have a high compression ratio car, you often have to use a higher grade of gasoline, as we're going to see next in the next slide. But the more power your car can pull, the more likely it's going to knock, because you have a higher compression ratio. Now, this is where we get to octane rating, or an octane number. Now, an octane rating is simply a measure of a gasoline's resistance to knocking. High quality mixes are used to prevent this knocking. Some molecules naturally resist knocking, like 2,2,4-trimethylpentane. Some organics have a very high likelihood of knocking, even at moderate conditions, such as heptane. We've labeled 2,2,4-trimethylpentane because of its unlikelihood to knock at 100, and heptane at its high likelihood of knock at 0. And so what we actually do is we compare a molecule to a mixture of these two organics. So what ratio of these two organics would give you this resistance to knocking? Now, there's actually two ways to compare these. One is the research method, and the other is just the motor method. The research method is how likely is it to knock with this molecule when you accelerate rapidly from a dead stop. You put pedal to the floor from a dead stop. And the motor is just how likely is it to knock while you're traveling at highway speeds. Neither of these are perfect, so we actually take an average of the two to calculate the octane rating. But all of these go into looking at the octane rating of a gas. Octane in itself has an octane rating of -20, so a high likelihood to knock. Pentane has an octane rating of 60. Regular gasoline is usually 87. Premium gasoline, 93. It said 2,2,4-trimethylpentane, 100. Ethanol, 105. Methanol, benzene. See, and some of these other molecules later have even higher octane ratings, like over 100. So they have a very low likelihood of causing knocking. Now, in the 1920s, the public wanted greater power, more fuel efficiency. They wanted the muscle cars. They wanted to be able to get a lot for that but they didn't want to have all this knocking. So we needed to up the octane rating without making things too expensive. Right now, at that point, trying to get branched hydrocarbons was too expensive, and we couldn't easily do that, which is why in 1922, Thomas Midgley, General Motors, found a quick, cheap additive that could achieve that. He found that by adding 0.1% of tetraethyl lead to the gasoline, he could increase the octane rating between 10 to 15 points. People could have all the power they wanted without having very expensive gasoline. So tetraethyl lead was just a chemical that was added to inhibit knocking. This, as we'll see, was not a good thing, but this is where we get the term leaded gasoline. If you ever heard of the term leaded gasoline, it was gasoline that had this lead additive added to it. As I said earlier, the ideal conditions, you should have CO2, water, and maybe some carbon char and carbon monoxide byproducts in gasoline. But this isn't always ideal. We often got the sulfurs going to sulfur dioxide and the nitrogen going to various nitrogen oxides, which were major pollutants at the time. So we get all these cars, and suddenly we get all this air pollution. We start seeing all the smog. Old LA, you could barely see in it because the smog was so bad. Well, in the 1970s, Congress passed the Clean Air Act, saying that essentially the auto industry has 5 years to reduce the CO emissions to 10% of its current value. So the cars produced in 1970, the 1975 models better produce carbon monoxide up to 1/10 of its original value, and also reduce the amount of sulfur oxides and nitrogen oxides and react with the unreacted hydrocarbons. So try to convert all the carbon monoxides and char into CO2 if all possible, which is where we first introduced our catalytic converter. The catalytic converter uses a catalyst, which catalyst, of course, is a substance that speeds up a reaction, but is not itself a reactant. So it does a reaction without getting used up, which is good. The catalytic converter had some platinum and palladium, as well as some other metals in there. And that basically this was a stop between the engine and the exhaust. So as the CO2 and all the byproducts pass through the catalytic converter, they would be converted into somewhat harmless intermediates, like convert all the carbons to CO2s, all the carbon monoxide to CO2s, and maybe change the sulfurs and the nitrogens so that it's less harmful as they come out of the tailpipe. Well, the problem is we had something called catalytic poisoning, that these guys are sensitive to other things reacting with them and then preventing the catalyst being useful. Well, that lead from the tetraethyl lead would then absorb onto these catalysts and block them. And if it blocked these catalysts, they couldn't do their job. 2 tanks of gasoline and you've just ruined a catalytic converter. If you've ever tried to replace a catalytic converter, that is not cheap. You do not want to be ruining catalytic converters left and right. And so Congress passed another law prohibiting the use of tetraethyl lead. So we had to find a new enhancer. Well, there's also another reason. Lead is kind of a toxin for humans. If you haven't already realized that it attacks the nervous system, organs, reproductive system, fetuses. It's kind of an all-round bad thing. Old houses still have to worry about lead paint. We used lead paint because it made a really brilliant white. Unfortunately, when the paint got old, it flaked off. And paint chips, lead is, I've been told, is rather sweet as metals go. And so children would eat the paint chips and they'd get severe mental retardation, that it would lower their IQ by like 10, 20 points. We've also seen that people used to use lead silverware. And if you had too acidic of food, it could dissolve off the silverware into the food. Same problem. We had issues called plumbism, coming from the Latin of plumbum, which was the original name of lead, which is why lead is Pb, because it's coming from the Latin plumbum. Lead is very sensitive to acids, as we can see in some that happened within our lifetimes, which is Flint, Michigan. Flint, Michigan, lead was in the water pipes. Well, I'd say, like, what? Why would you put lead in the water pipes? Lead is a cheap soldering agent, and it's a good coating agent. It's usually really safe in neutral water. Neutral water. We had lead in almost all the pipes. It's a lot cheaper than the alternative of copper. But the issue here is they switched water sources. They switched from one water source, which was relatively neutral, to a different water source that had a different acidity. And when they switched to the water source, it dissolved all the lead within the pipes, among other things. And suddenly the pipes started to corrode, and all the water then became highly toxic. And we're still working on replacing that and making Flint safe again for people. This is not only a Flint problem, but this is a lots of places problem. But Flint is one of the key towns where this is very well documented. The lead in tetraethyl lead can also be released through the tailpipe as a gas, which is also kind of toxic. The book kind of poo-poos it to some extent, but it's been well documented that people inhaling this gas will go insane. That workers in the factory that's preparing tetraethyl lead, some of them would go insane and die while working because it spray out and they'd inhale too much of it. That tetraethyl lead, maybe not the best of additives. Cheap, but not the best. Well, thankfully, we figured out a better one, which is methyl tert butyl ether, which also has some of the same effect. It's also an octane enhancer. Well, so octane enhancer is a gasoline additive used to increase the octane rating. So just like tetraethyl lead, this MTBE is an octane enhancer. This is an ether. We kind of talked about ethers briefly last chapter, but an ether is a compound in which oxygen atom is bonded to the carbons of two organic groups, which may be identical or may be different in structure, but the idea is oxygen bound to two separate carbons. The other advantage of MTBE is that it's an oxygenate. It's a gasoline additive that contains oxygen and may improve the efficiency of hydrocarbon combustion. Basically, if there's not enough oxygen mixed in with the fuel, we'll produce more carbon monoxide, like we saw at the end of last chapter. But if we have more oxygen, we're going to see a complete combustion to CO2. Well, these oxygenates will add extra oxygen, so we'll get a better combustion and more power. Congress made an addendum in 1990 to the Clean Air Act that requires that we have at least 2% oxygenates by mass into the reformulated gasoline. Now, MTBE contains 11% by mass. And by 1999, it was in 87% of all reformulated gases. But once again, MTBE sounds like a good idea until it isn't a good idea. We found, because of its unreactivity for the most part, it burns, but it doesn't really decompose. That because of that, it would occasionally leak into the groundwater. Gasoline is stored in large underground tanks at a gas station. If any of these were to leak, they could leak into the groundwater supply. And while the oil would float and be easily separable, this, because of its etherness, the oxygen would dissolve into the groundwater and be present, and thus cause certain problems in people's health. And it was hard to get rid of it. And so we wanted to avoid poisoning ourselves again through a different source. So in 2002, California banned the use of MTBE. 2004, New York did. And since they were the largest consumers of this, it slowly has petered off. Point where 2007, 25 states have banned this. we now, of course, use ethanol as our oxygenate source. We use up to 10% ethanol by volume in most cases. This is a little bit safer. It's also, as we know, renewable because we can make this from corn. And of course, the farmers like this because they can then subsidize their corn. So let's look back at the crude oil now that we've looked at all of our petroleum. Well, in the crude oil, we would then distill this. We would distill this through a fractional distillation tower, a fractionating tower. Basically, run it through a furnace, which heats all the crude oil up. And then we go through various different chambers, giving each fraction a chance to condense in the chamber. The hotter fractions will travel farther up into higher and higher chambers until they can escape out the top. The lower one, the cooler ones will condense into certain regions. So the low boiling hydrocarbons would just escape through a gas. The straight run gasoline would end up near the uppermost chamber. Kerosene would end up in the middle. Heating oil, diesel fuels, and jet fuels would go near the bottom. Would have lubricating oil and paraffin wax in the last chamber. And the solid asphalt and tar can be drawn off as a residue. So we're essentially boiling them up and separating them based on the heat. In the demo I did, diethyl ether boiled at about 30 degrees. So while everything else stayed liquid, that would have escaped first. Then the methanol boiled at about 70 degrees. So that would escape next. So that'd be a middle one. And then, of course, the water would boil at about 100, and so that would escape last. So we can use this to separate our straight run gasoline from our methane and all the other things. Boiling range of 4 to 12, it boils below 200 degrees. There's our kerosene, straight run. Kerosene, which is the next level up, 10 to 14, boils at about between 150 and 275. Then heating oils, anywhere between carbon 12 and carbon 20, boils between 175 and 350. So these are going to get a little mixed together. Then lubricating oil, paraffin wax, carbon 20 and above, somewhere between 350 and 550. And the residue doesn't really boil. It's just left over. It's the heavy carbons. Straight run gasoline by distillation isn't really enough for what we need, our purposes. For our today's fancy gasoline, we need more of this stuff. Even in the best crude oil, there's not much more than 20% of straight run gasoline in this blend. Though we do get a lot of kerosene as well. Now, kerosene was an important product in the early 1900s when there wasn't many cars. This was our heating, one of our things we used for heat and our lamps. So we used kerosene all the time. Gasoline was just a added bonus. Kerosene was what we really wanted. But as we got more and more cars, we've quickly outstripped the gas supply. And we were quickly running out. We couldn't fractionate this fast enough. But before World War I, catalytic cracking was invented. Essentially, we could take a large molecule and crack it into smaller molecules. We can crack carbon 12 kerosene into a hexane and a hexene, 2 carbon 6s. We crack it perfectly in half. We can break it down. So using this, we can turn a 20% of straight run gasoline into closer to a 50% straight run gasoline at the expense of the higher boiling hydrocarbons. So if we're willing to lose some of our kerosene and lose some of our heating oil, we can produce more straight run gasoline. Of course, we have to run a very careful tightrope because on cold winters, we need more kerosene. But on mild winters, we're probably going to need more gasoline. So do we crack more kerosene or leave the kerosene where we need. And so the government and companies have to kind of judge what they think the weather's going to be and use the strategic reserves very carefully so that we don't run out of one or the other and see the prices skyrocket. In addition to that, we can do a lot of new catalytic processes, catalytic reforming, to change our molecules around into something better. Catalytic reforming is a process by which our hydrocarbon molecules are reorganized into more useful structures with the same carbon content. We can turn straight carbons into branched carbons. So some of these processes include isomerization, where you turn a straight hydrocarbon into a more branched version. We essentially kick the carbon from the end and put it in the middle. So we move this around, move this to here to make a branched hydrocarbon, thus changing its octane rating. We can cyclize these guys. So we could turn a saturated hydrocarbon into unsaturated cyclic hydrocarbon through cyclization and produce some hydrogen gas in the byproduct. And we can take a cyclic hydrocarbon and turn it into a aromatic benzene ring through a process of aromatization, which produces more hydrogen. But of course, benzene has a higher octane rating. These benzene rings is a type of jet fuel. If you add some carbons onto here, you can have xylenes, which are a common jet fuel. So you can get higher octane ratings that burn better. So all these are processes by which we can modify gasoline. So this is a really neat field where there's lots of science going on, and it apparently pays very well if you're willing to work for these companies. I won't say it's the most exciting work, but it is clearly a very necessary work. Hello once again. Hopefully this chapter gave you a better appreciation of our everyday world, how we can simply turn this hydrocarbon into a fuel source, and how we use this to power our everyday lives, how we can manage to take dead dinosaurs and turn them into something that is useful. The process of petroleum distillation and processing makes all sorts of chemicals that we use in everyday life. Whether you realize it or not, those petroleum distillates will be the feedstock to make just about any type of plastics you need. Any polymers, as we'll see later on, comes from these simple feedstocks that we can crack the carbons down small enough, and then we build them back up in a very regularized pattern, and suddenly we have polypropylene or polyethylene or polyvinyl chloride, and each plastic having different properties that we utilize in our everyday life. How this chapter shows us how science has constantly been a struggle to improve our lives while not ultimately making it worse. A lot of times science gets some things wrong, and we have to keep on fixing things. We don't always have the chance of having foresight of knowing what this is going to be, and we don't have the time to fully study this out. It'd be nice if we could take years to study what the effects of mixing this chemical in will do, or what the effects of building this pipeline. We don't have the modeling program, we don't have the virtual world that we can check and perfectly expect what's going to happen. So our engineers, our politicians, we jump forward, try something, and then spend our time fixing that later, trying to correct our mistakes. That's a bit of life, but that, c'est la vie. That is what we have to deal with as being a human. We constantly strive to improve, but sometimes it's not doesn't always work in our favor. Now that I left you with a downer of a thought, I'll leave you and we'll talk more for next chapter.